done. Seniors, you guys can work on your stuff that you might have to still work on. 2:45 is the deadline, so make sure you get your stuff in 2 weeks before then. Do as much as you can. Yes, sir?
Do we have a test on this unit?
We will.
Okay.
Yep. This will probably be the last one, and everything after that will just be final only. Would be my suspicion for our last, about a month left from here, or from yesterday. I think it's exactly 1 month from yesterday. So that'll be my plan. We'll do one more unit, we'll do test on that, and then anything we do after that will be final only. So for this unit, we're gonna be talking about sequences and series. So today we're gonna start talking about sequences. We'll probably take a day or two more to finish up talking about sequences and then kind of start talking about a series. And maybe a day or two on series. So probably, another week or so of lessons and we'll be out on this. It's not it's an incredibly deep topic, but we don't need to go very deep into it. So let's just start with some basic definitions. So a sequence we define as a function from the natural numbers to the real numbers. When we say natural numbers, what are we talking about here? What's a natural number? Positive whole numbers. So 0, 1, 2, 3, 4. Okay, no negatives, no decimals. Everybody's okay? Okay. So the way we might represent a sequence, we can represent it as a list of terms. So for example, the sequence, 2, 4, 6, 8, 10, etc. is a sequence. What's up, Addie?
Do you have an extra pack? I left mine at home.
Right there on that desk. You're welcome, dude. Good luck.
Thanks.
Okay with that? So you can just list it as you can write a sequence as a list of terms. You could write it as an explicit formula, like a sub n is equal to 2n. Now, as far as notation goes, when we describe a sequence, this subscript identifies the term number, and this over here represents the term value. So for example, we would name the terms in this sequence. Well, this is the first term, the second term, third term, fourth term, and fifth term. So if we called this sequence a sub n, 2 would be equal to a1, 4 would be equal to a2, 6 equal to a3, and so on and so forth, right? Is everybody okay with that? So if we want to talk about the 10th term in that explicit formula above, means we're talking about a10. So we're going to take the 10 and plug it in to the formula, and out spits the value of the 10th term. Everybody's okay? So if we think about this as a function, like a f of x equals, the input to our function is the term number. That's like the ordinal number, like what it appears in a sequence, whether it's first, second, third, fourth, fifth, sixth, etc. And the output is the value in that place. So in our example above, 2, 4, 6, 8, 10, those would be like the term values. So again, the fourth term is 8, or the fifth term is 10. Does everybody feel okay with that? So all we're kind of covering right now is vocabulary, notation, how to represent these things. We haven't really done any problems yet. We're just kind of talking and developing a language that we're going to use to describe these things. But I want to point out to you that this explicit formula is essentially like a function notation, right? Instead of writing f of x, we write a subscript n, and then we write equals, and then instead of writing it in terms of x, we write in terms of n. But it works the exact same way. You can think about plugging values in for n, and out spits the value or the term values for the sequence. The n's that you can input have to be natural numbers because they are like ordinal values for where does this term appear in its sequence of numbers, whether it's first, second, third, fourth, fifth, sixth, etc. Does that feel okay to everybody? Okay. The third way that we can represent a sequence is with something called a recursive formula. So we call it a recursive formula because it's built on using our previous results. It works recursively. So for example, say we have the recursive formula a sub n equals a sub n minus 1. So I would think about that just as the term before, maybe like one term before. A sub n minus 2 is like two terms before. And then whenever you list a recursive formula, you need to give a starting location. So if this particular recursive formula requires the previous two terms, so my starting values have to include two terms, right? The first two terms. If my recursive formula only included one previous term, then I could just start with the first term, but I have to give it a starting values. So we're told here the first term is 1 and the second term is 1. So the third term says, or the formula for A3 says it should be the term before plus the term before that. So that should be 1 plus 1, so that should be 2. A4 says it should be the term before and then the term before that. Well, that's 2 plus 1, so that should be 3. A5, well, that should be the term before plus the term before that. So that would be 3 plus 2, that's 5. And you can continue building this thing on in the similar manner, right? Just taking the previous two terms and adding them together. What do you notice that when I compare explicit and recursive formulas, if I want to find the 1,000th term using a recursive formula, what's the disadvantage there?
It's a lot of...
You have to find the 999 terms before it, right? You're going to have to build there. If I want to do that for the explicit formula, I can just drop 1,000 into n and be done, right? So in some ways, the explicit formula is much more convenient to use, right? So why have a recursive formula? What advantage does that have? There can be some sequences where the recursive formula is quite easy to write, but the explicit formula is quite difficult to come up with. The sequence here that we've listed, where the sequence is the sum of the previous two terms as a recursive formula, this actually is a famous sequence. It has a name. It's called the Fibonacci sequence. If you've read the Da Vinci Code, this is featured prominently, or if you're an art fan, if you study like art theory, the Fibonacci sequence comes up in that because of its relationship to the golden ratio and the Archimedean spiral. Yes. Well, the explicit formula for this, that turns out there is one, it contains an irrational number, which is strange. In fact, two irrational numbers. I think it's 1 plus root 5 over 2 and 1 minus root 5 over 2. And coming up with that is actually, from an original standpoint, is quite a difficult problem. You end up having to resolve it into a quadratic to find the term, like the factors that you need, and it turns out to be exponentially based, which is kind of strange. But coming up with the recursive formula is quite simple, right? We're just adding the previous two terms. Coming up with the explicit formula is quite complicated. It's like a graduate level mathematics problem. So that's the main advantage of recursive formulas, that they are easy to describe some sequences that are really difficult to describe explicitly, even though they're not convenient to use if you want to iterate a bunch of things. And then the fourth could be just looking at a graph. So for example, if I wanted to graph that very first sequence we looked at, 2, 4, 6, 8, etc. So I'd have like 1, 2, 3. So I'd graph 1, 2, where the x-axis is my term number and the y-axis is the term value. And then we'd plot 2, 4, and then like 3, 6. Do I need to connect these? Should I connect this? No, why not?
Because there's no numbers in between the points.
Correct. So if you remember, the domain is the natural numbers. There are no inputs in between, so these are just going to be discrete points. The graph of a sequence should always just be points. Now, it could look like a line, right? I could draw a line that goes through all these points. That's fine, but we never connect them. So far, so good? So the four ways to represent a sequence. You could write it as a list of terms. You could write it as an explicit formula, a recursive formula, or as a graph. Okay? We're going to start by talking about two special types of sequences. The first one is called an arithmetic sequence. We define an arithmetic sequence because the terms in that sequence have a constant common difference. We represent that number with the letter D. So if I look at my example sequence here, 2, 4, 6, 8, 10, I notice to go from 2 to 4, I've added 4. To go from 4 to 6, I add 2. To go from 6 to 8, I add 2. 8 to 10, I add 2. That tells us that I have a common difference of 2 and that this is arithmetic. Is everybody okay with how I did that? Very easy to do, right? You just have to see in a couple of the examples. Let's look at this next sequence. So this is 1, 4, 9, 16, 25. So if I tried to do the same thing here, what do we notice? Well, there's a pattern, right? But this is not good enough. It's not constant, right? It's a different number we're adding each time. Even though there's a pattern, if it's not constant, it's not an arithmetic sequence. This would actually be like a quadratic sequence. You might recognize those numbers as all perfect squares. So the formula, the explicit formula would be like a sub n equals n squared. Okay. The other type of sequence that we'll talk about here in the beginning is a geometric sequence. So geometric sequences have a constant common ratio that we call R. So arithmetic sequence, we're going to be adding between the terms. For a geometric sequence, we're going to look for multiplication between the terms. I notice that if I take the previous term and multiply by 2, I get the next term. That tells me in this case my R is 2. So this would be geometric. Everybody's okay there? Let's look at the sequence 100, 50, 25, 12.5, 6.25. What's the pattern that's going on here? What do you guys see? Dividing by 2. Is that arithmetic or geometric or neither? It's geometric. Why, if we're dividing, is it geometric? Can I write division as a multiplication problem?
Yeah.
Yes. What is dividing by 2 the same as?
Times by 1/2.
Multiplying by a half. Oh. Don't be confused. We could do the same thing with arithmetic if we were subtracting. We just think about their adding by a negative. Is everybody okay? So even though it's division, that's no big deal. You can still think about it as multiplication. So it still counts as geometric. All right. Again, the question here is arithmetic, geometric, or neither? Go ahead. What do you guys think? Here's the sequence. 0, 3, 8, 15, 24. Well, let's try. If it's arithmetic, I can stop right there, right? Because the first two are not the same addition. And I know that there's nothing I can multiply 0 to get to 3, right? So this just has to be neither. Right? Nothing I can multiply by 0 is going to get me 3. So immediately I can see it's not geometric. So again, if it's a neither, we just try both. And if neither of them works, then that's your goal. There's no like, oh, if it looks like this, then it's neither. We just do it by exclusion. Right? If it's not geometric and it's not arithmetic, then it goes into the neither category. How about this next one?
Geometric.
Good. What is the R?
3.
Yeah, that's exactly right. Each time we're multiplying by 3. How about this one? What about C? Oops, I'm missing a denominator there. That, right? Nope. 6. Sorry. It's a little bit harder here, right? You know what's going to make this easier?
Mixed numbers.
A common denominator.
No.
What would the common denominator be between all of these things?
6.
6. So if I do that, I rewrite this as 12 sixths, 11 sixths, 10 sixths, 9 sixths. That should be, I guess that one should be a missed one here, huh? Should be 8 and then 7 sixths. Oops. Oh, should be 4/3, right? There we go. Okay, 8 sixths, 7 sixths, 1 or 6 sixths. Now it's quite clear, right? So if you're given fractions and it's not clear what's going on, try making a common denominator and see if that helps, right? We could do something similar up here with the geometric, right? This is like 3 to the negative 2. This is like 3 to the negative 1. This is like 3 to the 0, 3 to the 1, 3 to the 2. So it's pretty clear at that point, oh, we're just multiplying by 3 each time. So you could think about it that way also. All right, the last thing I want to do today is talk about how do we write formulas for arithmetic sequences. We'll do geometric a different day. We're just going to talk about arithmetic ones today. So we're going to do explicit first, and then we'll come back and do the same problem and write the recursive sequence. So the explicit formula for a arithmetic sequence is a sub n equals d times the quantity. Go ahead. Go ahead. Sure. Yep. D times n minus k plus a sub k, where d is the common difference and a sub k is the kth the kth term of the sequence. Everybody's okay there? I guess we should say like maybe k comma a sub k. All right, so let's look at a sequence here. So we have 7, 9, 11, 13, 15. Is this arithmetic? Yeah, right? Should be easy to see that right away. So there's my d. That's d equals 2. And then I need a term, right? Well, I'm going to choose this guy. Does it matter which one I pick? No way, Jose. So it tells me the first term is 7. So when I fill this in, I'm going to say 2 times n minus 1 plus 7. Or if I distribute things out and combine my like terms, there's my final answer, 2n plus 5. Now that we've done this, what does this explicit formula kind of remind you of? What does it kind of look like? It looks like the point slope equation for the line, right? Where this would be like y minus y1 equals m times x minus x1. And in fact, it is. We've just renamed x as n, x1 as k, y1 as a sub k, and m as d.
Is k always 1?
Nope, depends on which one I picked, right? If I had picked this one, this guy would have been A4 is 13. Yes. So there, if I had chosen to use that one, I would write n minus 4 and then plus 13.
It just depends on where the number you pick is in the sequence.
Just depends on the number you pick or what's given to you.
Yeah.
So we'll see another example where like you have, like you're just given certain, instead of giving the whole sequence, you're just given part of it. Yes, sir.
It doesn't matter what number you
In this problem, not at all. And in fact, in general, it does not matter. Is everybody okay? I would just pick the first one because the arithmetic's easier. Okay, what if you're given a problem like this, where you're just given the 5th term and the 10th term? Now you're told it's an arithmetic sequence, and you have to be given that. If you weren't given that, then this problem is not possible. So what am I going to do? Well, I'm going to remember that this is basically the same thing as an equation for a line, right? Where the slope is the same thing as d. So these two terms I can think of as points, right? Where this is like k comma a sub k. So if d is the same as slope, I can just do y2 minus y1 over x2 minus x1. There's my slope, right? Now, does it matter which point I use? Not even a little bit. So say we use this one. And then I can just distribute the 3 through and combine some like terms. Oops. and I'd be done. Could I just have easily used the point 10 comma 25? Yeah, right? There's no difference. You'll get the exact same answer. The arithmetic's worse because the numbers are a little bigger. But I would just pick the point where the arithmetic looks the cleanest. You know, it doesn't matter. So whatever one looks easier, use that one. Right? If you can avoid a fraction, pick the one that doesn't have a fraction in it. If you have one with smaller numbers, pick the one with the smaller numbers in it. You know, doesn't matter. So do what's convenient. What do you guys think on this? Is this okay? Again, fairly easy, right? It's basically just writing the equation for a line, which you've done, I don't know, in 7th grade, 8th grade, 9th grade, 10th grade, 11th grade. I think you've done it like 6 years in a row or something. Should be pretty decent at it. This is the same idea, just we've renamed the parts n and, you know, n and comma a sub k instead of x, y, but it's the same process. It just has a different names on things. Okay. If this was a recursive formula, so the recursive formula says it's going to be the previous term plus that common difference, and we have to state the first term. So let's look at the same sequence again. This is the same problem as before. We're just going to write the recursive formula instead of the explicit. So the d equals 3. And then I have to list the first term, which in this case is 2. And there's my answer. I'm done. How easy was that? Mr. Kulik, that was pretty easy. Okay. Where it gets a little bit trickier is if I am doing the same thing for this problem. So, to find the d, I got that, right? I do it the same way as we did before, right? You basically use the slope. And then to find the first term, I'm going to use the explicit formula. I'm going to have to have written that first. Let me actually really do this. So unfortunately, if you're given just the two terms and you want the explicit or the recursive formula, you need to have written the recursive one first so you can find the first term. There's not a great way of doing that other than using the explicit formula, which isn't really that hard to write, let's be honest. And most of the time on a test or quiz or whatever, you'd be asked to give them both anyway. So like once you got one, the other one's pretty easy to generate, right? This is where I'd like to stop. This is enough for today. Your guys' juniors, your assignment from this is just this delta math that I threw together. So there's just 4 categories of questions. So here it says find the common ratio for the geometric sequence. So you just have to figure out what R is. Everybody cool with that? In this case, it's going to be just 126 divided by -18. Done. Type in your calculator, put the answer in there, and then go. Here's common difference. So we know it's arithmetic. Now, here we've been a little bit trickier in giving you the terms of your sequence as polynomials, but this isn't bad, right? If I look, the constant term stays -1. The thing that's changing is the variable term. So I'm just looking at 7x to 8x to 9x. What's going on here? We're just adding x, right? That's pretty easy. Here we're asked to find the 53rd term of the arithmetic sequence. So I'll write the explicit formula, just like we did in the notes, and then plug the 53 into it, and then type in whatever the number is in here. We're good. And the last one is here, which is the same idea, except instead we have terms that are polynomial, but we'll approach it the same way. I'm going to write my explicit formula. It'll have an x in it. That's fine. So it'll have n and x. We'll plug in, then after we have our formula, we'll plug 9 in for n, and then do some combining like terms or whatever and type in our answer. We're done. Okay? So it's that's it. It's those 5 questions, or those 4 types of questions, 5 each. No penalty for wrongs. Delta Math estimated this was like 30 minutes, which usually they're a little high on their estimates. This, I think, should be pretty quick. We'll tack on some more to this eventually, but I think this was good for one day, especially this last chaotic day. I'm going to be done talking now. You guys are free to relax, start your Delta Math, visit with your senior buddies on their last day, work on something else that's higher priority to you, or generally be undisruptive.
Go, sir, go.